Okay, so welcome to the first presentation on the new topic of momentum. In this lesson, we're going to look at what we mean by momentum. We're going to take your understanding from year 10 and move it on, hopefully. And then we're going to look at what we mean by this quite funny idea, or funny word at least, of impulse. So what is momentum and how do we calculate it? And what do we mean by an impulse? So to define momentum, we need to look at a couple of Newton's laws, Newton's first and Newton's second law. Newton's first law, we looked at this a little bit in year 10. Newton's first law, an object remains at rest or in uniform motion unless a force acts on it. This is the idea that things keep doing what they're doing, the idea of inertia. You may have looked at that in a video clipping lesson. If something's stationary, it's going to remain stationary. If something's moving at a constant speed, it's going to remain at a constant speed. Things don't speed up or slow down on their own. A force has to act. Okay. Newton's second, this is the F equals ma law from year 10. The rate of change of momentum of an object is proportional to the force on it. Now that does not sound anything like force equals mass times acceleration, but let's just look at what it says and take it apart a little bit more. I've written here that force is equal to the change in momentum divided by the change in time. Now that is a rate of change of momentum. If the rate of change of momentum, I'm just going to rewrite that, and instead of saying delta momentum, I'm going to say it's the final momentum, mv, minus the initial momentum, mu, and that will be the change momentum. I'm going to still divide that by the time. A little bit of algebra, I'm just taking out the m, so removing the m outside the brackets, then suddenly my equation becomes m in brackets v minus u, final minus starting velocity, divided by t. Hopefully you can see from year 10 that v minus u over t is acceleration. So F equals ma, and you're back to your year 10 equation. But the year 13 equation is F equals delta mv divided by delta t. Just a little quick note, you might see this delta in different places. Here I've got a change in velocity caused by a force, and here I've got a change in mass caused by a force. So it's an m delta v. It's an m delta v or a v delta m. A couple of examples to think about. It's nice to think about real life applications of where you can apply this equation. If you imagine hitting a tennis ball, when you hit a tennis ball, or even in any other sports where you would hit a ball, you don't just sort of stop the bat at the point you hit the ball. You sort of follow through and you keep the bat in contact, or the racket in contact with the ball as much as for as long a time as you can. So what you're doing here, you're increasing the force on the ball, because if we just rearrange our equation as delta mv equals f delta t, so I've just moved the delta t up. If I increase delta t, then my f times delta t with a bigger delta t gives you a larger change in momentum, and that's obviously what you want if you're playing a game. You want to get that ball moving and change its momentum as much as you can to get it back over to the side of the court. The flip side of this, if you're catching a ball, when you draw the ball back into your body, if you ever caught a cricket ball or a rounders ball or something like that, you may find that you draw it back into your body. This is because you want to reduce the ball's momentum, because you've got to stop it, but you want to do it over a longer period of time. So if you look at the equation in this form, if you change the momentum over a long period of time, if you increase delta t, then you're going to reduce the force. This delta mv is fixed. You've got to stop the ball from whatever velocity it's going at, but if you do that over a longer period of time, then you will reduce the force on your hands. Okay, so this idea of impulse, what do we mean by an impulse? The equation for impulse is probably it's a rearranged equation. You are given both. So F delta t equals delta mv. So this sort of bit of the equation, the change in momentum, that's all it is. That is what is called the impulse. So the impulse is the change in momentum. So you can see the impulse is equal to force times the time for which it acts. What you can do with this is apply it to a graph of an object undergoing a force over a time. So here I've got a very basic graph of a golf ball being hit. If you imagine if you start the clock at some time here, the golf club will make contact with the golf ball, so the force on it will increase. The shape of the golf ball will probably change as this occurs. That's a little bit of material science happening, but the force will reach a maximum, and then as the change of momentum of the ball causes it to move away from the club, then as it loses contact, the force will reduce to a minimum. So a force time graph would look something like this. Indeed, most force time graphs have this shape. A force acts, it reaches a maximum, and then it reaches a minimum and stops acting. Now, for something like this, you've got to almost average out the forces. You've got to think about that force acting over all this time. I can't say that the force acting is this value here. I would have to sort of average out all the forces, or I'd have to add up all of the little force times. Now, that is a process of integration, which I'm not going to do, but you can just say it's all of the little strips of force time. So you can see that little strip there. If I worked out the force times the time for that and then did the next and the next and the next, I would add up all of the little force times time. So that would give you a total change in momentum, or a total impulse. So the key thing is the area under a force time graph is equal to the total impulse, or the total change in momentum. If we just do a couple of quick questions, these are quite simple, straightforward questions to get you started. What is the impulse produced by a force of 4 newtons acting for 3 seconds? So if I use this equation, the impulse is the delta mv. It's simply 4 times 3. So force times the time is 12 newton seconds. The units here, just a quick note on the units. The units of change in momentum can be in kilogram meters per second, or they can be in newton seconds. Both are valid. What effect does this impulse have on a stationary mass of 2 kilograms and 3 kilograms? Well, if we've got a total impulse of 12 newton seconds, which, as I've said here, is 12 kilogram meters per second, it's just the same. I'm sort of saying that if I apply that impulse to a 2 kilogram mass, then I'm going to say that 2 times v, or my mass times velocity, the change will be equal to 12. So 2 times something is 12, my change in velocity is 6, the mass is constant. And here I've done the same. 3 times v, mass is constant, so my change in momentum is going to be equal to 12 again. With a 3 kilogram mass, 3 times v equals 12, so v must be 4. If we look at a train of mass 24,000 kilograms moving at 15 meters per second is stopped by a braking force of 6,000 newtons, what is the initial momentum and how long does it take to stop? Well, the initial momentum is mass times velocity, so it's 15 times 24,000. Gives us an answer of 3.6 times 10 to the 5 kilogram meters per second. And how long does it take to stop? Well, for that we'd have to sort of rearrange this. We'd have to rearrange this to say that delta t equals the change in momentum divided by the force. So I've rearranged that to give me the change in time, change in momentum divided by the force. And 3.6 times 10 to the 5 divided by the 6,000 newtons braking force gives me a total stopping time of 60 seconds. Last one, very similar question. An aircraft of total mass 45,000 kilograms accelerates from rest to 120 meters per second. In this time, its engines provide a force of 120 kilonewtons. What's the gain in momentum, and what is the takeoff time, assuming it takes off in this question? The gain in momentum, quite simple, mass times velocity, 45,000 times 120 gives us a change in momentum, or gain in momentum of 5.4 times 10 to the 6. Using this rearranged equation, my time is going to be change in momentum divided by the force. So this time it's 5.4 times 10 to the 6 divided by 120,000 gives me a takeoff time of 45 seconds. Finally, a couple of multiple choice exam questions just to finish us off. Here we've got a classic question on using a force time graph. A force varies with time t as shown by the graph and is applied to a body initially at rest on a smooth surface. What is the momentum of the body after 5 seconds? So we know that the change in momentum is equal to force times time. I just need to do an area under this graph. If I do the formula for a triangle, base times height, and then halve that. So I've 5 times 10 is 50, and I'm going to halve it to hopefully give me an answer of 25 newton seconds. Then this is quite a slightly stranger question. The rate of change of momentum of a body falling freely under gravity is equal to its weight, power, kinetic energy, or potential energy. If we look at the formula, the rate of change of momentum is this formula. This is the rate of change of momentum, and we know that's equal to the force acting. The force acting in this situation is the body's weight. The units of weight are obviously newtons, power, kinetic energy and potential energy. The units aren't newtons, so we know the answer must be weight.